so the first thing we want to do in this problem is get our three tension vectors, TAD, TAC, and that T200 here, in Cartesian form. So, we'll do the T200 first. Now here we're actually given the direction cosine angles. The 60 here is my alpha. It's between the positive x-axis and my vector. This 40 degrees right here, that's going to be my beta, because it's between positive y and my vector. The only thing we're missing is gamma, the one between the positive z and the vector. So we can use this equation to solve for gamma. Alpha is 60 degrees, beta is 45 degrees. Yeah, this is a 45 right there. Alright, so if we do this math, we'll get our gamma. But you have to be careful, because when you work that algebra, you get down to this. And of course we have to take the square root, which means we're going to get a plus and minus version. So if you take the radical of 0.25, we'll get positive 0.5, but we'll also get negative 0.5. And of course both will give us two different gammas. The inverse cosine of that first option will give us 60 degrees, and the inverse cosine of the second option will give us 120 degrees. Now, you have to look at the picture to figure out which one is the truth, which one is actually happening. And if you notice this black line there, this one right here, the way it stretches, it means that it's an obtuse angle, one that's bigger than 90. So this 200-pound force vector is really sort of extending into the page rather than out of the page towards us. It's really extending in the negative z direction rather than the positive z direction. And again, that's all because of this sort of obtuse angle arc symbol right there. So gamma is going to be the 120 degree option. So of course, because this vector's direction is given by its direction cosine angles rather than a double projection sort of approach, we can sort of vectorize this vector using this. Each one of these is the magnitude, the length of the vector, 200, and of course we have our direction cosine angles. So let's just write this out for this 200-pound force vector. And of course, we can just crunch each of these into one number. So let's do that. So we're getting 100 for the I, 141.4 for the J, and a negative 100 for the K. And just always make sure the numbers match the picture, the visualization. Like we talked about, this 200 vector is sort of pushed into the screen, into the negative z direction. So it makes sense that its z component is negative. So because the question says that we know the tension in AC, we'll write that vector in Cartesian form next. And here it is, AC. We know the length of this vector, the magnitude, is 150 pounds. It looks like the direction of this vector is not given with alpha, beta, gamma, but instead sort of more double projection sort of way, double projection angle, as you might say. We're going to focus on this right triangle here. So we know here's our vector, 150. It's this hypotenuse right here. And we can use the sine of 60 degrees to get this opposite side, which will be the y component. So that's really easy. It's just one step. Let's just do it. So I'm going to say TACY, the y component of TAC, will equal 150 times the sine of 60. And if I do 150 times the sine of 60, I'll basically get 130. But you got to be careful. Always make sure your math is mirroring the reality. Is this a positive y component? No, it's not. That y component is clearly negative, pointing downwards. So we'll want to put a negative j hat. So we can continue to work this right triangle, and we can get the adjacent of that 60-degree angle. 150 times the cosine of 60 will equal 75. So that's the length of this line right here. But this is neither the x nor the z component, because it's not completely in the x direction, nor is it completely in the z direction. It's really in both directions, and that's why it's known as the double projection. So this 75 is this right here. And I can break this into a right triangle based on this 20-degree angle. And the adjacent will be the x component, and we'll use cosine to get it, and the opposite will be the z component, and we'll use sine to get it. So the x component of TAC will take that double projection line, we'll take that 75, the hypotenuse of the triangle that's sitting flat in the xz plane. Just know that we're dealing with another right triangle now. It's this one. And it's sort of flush, it's flat with the floor, the xz plane. So we'll do 75 times the cosine of 20 to get that blue adjacent side, and that's the x component. And that'll be 70.5. Now, is it really positive? Yes, if we look at that blue line, we can see that it's pointing in that positive x. And looking at the green line, which is the z component, look where its arrow is. That's pointing the negative z. So that'll be a negative z component. We can already tell just by looking at the picture. So the z component of TAC will equal 75 sine of 20, 25.7. We have to put a negative on it. So this is our negative z component, and the 70.5 was our x component, which is positive. So all in all, we have assembled the x, y, and z components of TAC. So now let's just write them all together. So now we'll focus on the tension vector AD. And it looks like the direction of this vector is again given in sort of a double projection sort of way. So I'll focus on this right triangle first. And here's our angle 36. And note that we don't know what the length, what the magnitude of this tension vector is. So we don't know the length of this hypotenuse right here. So I guess we'll just have to write everything in terms of unknowns. So let's go for the adjacent right here, and that'll be the y component, and again, this one will be a negative. So the y component of TAD will be a negative, and it will be the hypotenuse, the magnitude, TAD, an unknown, times the cosine of 36. Next, we'll go for the double projection line, this one in green. So the dp, the double projection, will equal the hypotenuse, TAD, times the sine of 36. So now we're done with this vertical triangle that's sort of standing up. So we'll now focus on the bottom triangle, in which the double projection is the hypotenuse. So here is the adjacent of this right triangle, and that will be the z component, and it will be positive. And this right here will be the opposite, which will be the x component. So we'll go for the z component first, the adjacent, and that will equal the hypotenuse, that double projection, the TAD sine of 36, times the cosine of our angle here, 48. And that purple line is pointing in the positive z direction, so it's going to be a positive k hat. And our y component was a negative j hat. And for the x component, TADx, still focusing on that same right triangle, it'll be our double projection again, times the sine of 48. And as we can see by that blue line, that's pointing in the positive x direction, so this will be a positive x component. And there we go. We have a negative y, a positive z, and a positive x. All written in terms of unknowns, but that's okay. So let's just write that out. And there we go. So now we get to this part. The resultant of these forces exerted at A must be contained in the xy plane. So remember, the resultant just means the sum. So I'll say R for the resultant must be contained in the xy plane. What that means is this resultant vector has no z component. It'll have some x component, some y component, and a z component of 0. And again, this is the resultant, the sum. We're going to add up these three vectors that we have fully prepped now. We're going to add their x's, and that's equal to the x component of the resultant, their y's, which is equal to the y component, and the z's, which is equal to the z component. Because remember, that's how you add vectors using the component method. So let's just write the math out for this. And as you can see, we have only three unknowns in this system of three equations. We have TAD, 1, Rx, and Ry. So we have three unknowns, and we have three equations, which means we have enough information to solve for these three unknowns. So in this case, it doesn't look too bad to do this mathematically. We can solve for TAD in this equation here, because that's the only unknown. And once we do it, we can stick it here to find out Ry. We can stick it here and find out Rx. So we get 319.6 for the tension in cable AD, negative 247.2 for the y component of the resultant, and positive 310.1 for the x component of the resultant. So we can just plop those right in here to complete our resultant vector in Cartesian form. And there it is. So the question wants the magnitude and the direction of this resultant. Well, the magnitude is just going to be the sum of the squares of each component. And if you do that math, you'll get 396.6 pounds. Now for the direction of this vector, this is a 3D vector, so I would assume when they say direction they mean alpha, beta, and gamma. And for those, don't forget, cosine of alpha will equal the x component of the vector, whether it's a force vector or a position vector or whatever, over the length, the magnitude of that vector. And same thing for the y component and z component. So if we do 3 inverse cosines, we will find our direction angles.